capacitor, and 1 resistor. A battery with EMF 120 volts is connected in series with a resistor and a capacitor. Switch S is closed for a long time and the circuit reaches equilibrium. Determine the charge on the capacitor when equilibrium is reached. Determine the energy stored in the capacitor. The spacing between the plates is doubled in an extremely short time compared to the time constant. Determine the work that must be done in increasing the separation. Then determine the current in the circuit immediately after the increase in spacing. After a long time, the current stops and equilibrium is reached. Determine the total charge that has passed through the battery after the spacing was doubled, and presumably that was done through some kind of machine because you clearly don't want to do this with your hands. And F, determine the amount of energy added to the battery. Determine the charge on the capacitor when equilibrium is reached, and that's after the switch was closed here. Equilibrium is reached when the capacitor is fully charged and the potential drop across the capacitor equals the EMF supplied by the battery. So C is equal to Q over delta V, that's our definition of capacitance. Q is equal to C delta V, which equals C times the EMF. Plug the numbers in, and we have a charge of 9.6 times 10 to the minus 4th coulomb. Determine the energy stored in the capacitor. We have our energy formula, 1/2 Q delta V. Again, we know that delta V is the EMF. Substitute in the values, and we get U is 5.8 times 10 to the minus 2nd joules. Determine the work that must be done in increasing the separation. Let's first find the capacitance of the new configuration in terms of the original capacitance. So C0, there's a definition for capacitance. And what have we done with the new capacitor? Well, it's the same capacitor, we've just doubled the spacing. Well, we go through some algebra here, and we find that we've cut the capacitance in half, so the new capacitance is 4 microfarads. In order to find the work done, we need to find the change in electric potential. But the capacitor is still connected to the battery. Doesn't the voltage stay constant? We'll answer that on the next slide. No. The key is the way the question was asked. The time frame is very short, so the charge on the capacitor stays constant, not the voltage. The voltage drop will immediately change, but after a long time, the capacitor voltage drop will once again equal the battery's voltage, which is probably what you expected on this problem, but there's the key phrase right there. So the new voltage drop across the capacitor is going to be Q0, the original charge which stays constant, divided by our new capacitance. Well, the new capacitance is half the original. Do some algebra, and then you find that the new voltage will be twice the original, so it will be 240 volts. Notice we didn't even need to use the new value of the capacitance. However, we still have more parts of the problem to go. So let's now find the new electric potential energy in terms of the original, and then finally we can answer this part. Work will equal the change in potential energy, right? That's the work energy equation. So U new is 1/2 Q delta V new. We know that Q stays the same, right? That's our original Q. And our new voltage is twice the original. So we carry on with the algebra, and we find out that the new potential energy is twice the original. So the work will equal U new minus the original. That's 2U0 minus U0. And we basically just get the original potential energy. So the work done is 5.8 times 10 to the minus 2 joules. The work done by the external force on the capacitor is positive since the electric potential energy increased. Determine the current in the circuit immediately after the increase in spacing. We already found the delta V once we increased the spacing, and that was 240 volts. The current will now increase from 0 amps because of the potential difference between the capacitor and the battery. So the current is going to equal the voltage across the capacitor minus the EMF of the battery divided by the resistance, that's just Ohm's law, put in our values, and we get 2.4 times 10 to the minus 4 amps. After a long time, the current stops and equilibrium is reached. Determine the total charge that has passed through the battery after the spacing was doubled. From part A, we found the original charge on the capacitor. After the spacing between the plates was doubled, the capacitance was cut in half. In the short term, the voltage changed, current flowed, and more charge was put on the capacitor. After a long time, when equilibrium is reached, what is the voltage drop across the capacitor? After a long time, the current stops flowing, and the voltage drop across the capacitor is once again equal to the EMF. So the final charge on the capacitor is going to be the new capacitance. Remember when we calculated that right in the beginning? That's 4 microfarads times the voltage final, which is 120 volts. So the final charge on the capacitor is this. The delta charge that passed through the capacitor is going to be Q final minus Q0. And we take our Q0, we calculated that earlier. So we have a negative delta Q on the capacitor, 4.8 times 10 to the minus 4th coulombs. That means charges flowed from the capacitor to the battery. After a long time, the current stops and equilibrium is reached. Determine the amount of energy added to the battery. The work done in separating the capacitor plates increased the electric potential energy of the capacitor. We talked about that earlier. Current then flowed from the capacitor to the battery, in effect recharging the battery and reducing the potential energy of the capacitor. So we're going to solve this by finding the electric potential energy of the capacitor, subtract that number from the energy added by the work done on the capacitor, and that will be the energy that went to the battery. There'll be some resistive heating losses, but we're not going to deal with that. The final electric potential energy of the capacitor, this is after 10 time constants have passed and all's done, is 1/2 times the final voltage times the capacitance, the new capacitance, which is the 4 microfarads. And we get the final energy in the capacitor is 2.9 times 10 to the minus 2 joules. We now want to find what happened to the battery. Well, the battery got the extra energy from the work done on the capacitor in separating the two plates. That's this term right here. So the capacitor had 5.8 times 10 to the minus 2 joules. At the end of our problem, it only has this much. So the delta energy, because of conservation of energy, went to the battery. We subtract them, and we find that the battery's energy increased by 2.9 times 10 to the minus 2 joules.